Welcome back from the break. We're getting back to the concept map, back to rates of reaction. In the previous sessions, we looked at the definition and the factors on a macroscopic view. We looked at the ways to measure rate. We also looked at graphs. And now I would like to go and look at the factors, but now I will link the factors to the collision theory on a microscopic view. So I just want to remind you that microscopic view actually means what we cannot see, but what we know according to the collision theory is happening microscopically. So we spoke about the factors affecting the rate of the reaction, and in an earlier session we said that temperature, surface area is specifically the surface area of solids, the concentration of solutions, meaning in solution where we use AQ, the pressure when we have gases. When we add a catalyst, we're specifically going to talk about a positive catalyst because that's what we do at school level. And then we should remember that the factors affecting the rate is also the nature of our substances, where we, for instance, said if you have an inert substance like nitrogen, gold, or platinum, they don't react very frequently. They don't really want to react. But if you look at your group 1 and your group 17 elements, they are highly reactive. And if you look at that nature, it will normally have a higher rate of reaction. The first question that I would like us to answer is, why does an increase in temperature, meaning when the temperature is hotter, why does it result in an increased rate of reaction? Now, you should remember that we said earlier that according to the collision theory, all particles are constantly in motion, and how fast or how slow they move actually is a factor of the temperature. Now, if the temperature is increased, we need to know that the temperature is a measure of the kinetic energy of a substance. And remember, the kinetic energy, where we know that Ek is equal to half mv squared. So when we talk about kinetic energy, we should then think about the speed of our particles. When we have hotter temperature or higher temperatures, we will have the particles will move at a higher speed because of the average higher kinetic energy that the particles will have. So the higher the temperature, the faster the motion of our particles. The particles will collide or bump or hit each other more frequently. So we will have more collisions per unit time. Remember, this per unit time is all to do with the rate of a reaction. And if we have more particles per unit time, we will most likely have more effective particles, more effective collisions per unit time, and then that leads to a higher rate of reaction, meaning a rate that takes a reaction that is faster. I just want to remind you again, when we talk about effective collisions, we're talking about collision where the kinetic energy is bigger than or equal to the activation energy. That's firstly. And secondly, there must be a correct orientation, meaning there must be an overlap in the unpaired electrons orbitals. The next factor that I would like us to look at is, or the next question that we have coming up is, why does an increase in surface area? Now, when we talk about surface area, I want us to know that surface area plays with the brain a little bit. So when we talk about a big surface area, we always think about something big. But the surface area that we refer to is actually the contact area of that solid, meaning how much contact area is in that solid that can collide or hit against each other or bump against each other. So the finer your solid, meaning if you have powder particles. There will be more space for the collisions to happen, and it will lead to an increased rate of reaction. So, if we look at what we have in front of us here, we actually have 1, 2, 3 from the front, 4 from the bottom, 5 at the back on this side, and from the back we have here 6 sides that is exposed to this reaction. But when we take that same piece, that same lump of your reactant, and you make it finer, you make it into powder form. Let's say every one of the small squares is a powder, a piece of powder granule. Then we can say if each one of them have 6 sides for collision or possible contact area, and we have 9 of them, we can see for the powder, we actually have 56 contact areas as opposed to the 6. That is why we say powder form is a higher or a bigger surface area as opposed to a lump. But you must remember, for a fair experiment, you must have the same mass of your reactant. When we have surface area that's bigger, if we look at this surface area there, it's a smaller surface area than the one next door. So if we have the collisions that take place, it takes place on the surface area, and like I said, we say it is the contact area. The larger that contact area, meaning the more possibility of contact, the more collisions will happen per unit time. And what do we know? When there's more collisions per unit time, we know there will be a likelihood of more effective collisions per unit time. And if we have more effective collisions per unit time, we actually have a faster rate of reaction. And then I know you can remember this, but I just want to remind you again. An effective collision is a collision where the kinetic energy is bigger than or equal to the activation energy. That's the first requirement. But there's a second requirement, and I know you know what the second requirement is. Yes, the second requirement is there must be correct orientation. When both these are met and we have many collisions happening, we will have a higher or a faster rate of reaction. And that brings us to the next question. How will an increase in concentration, why does that increase in concentration result in an increase of the rate of the reaction? Again, when we look at concentration, we should think of the following. Concentration is equal to the number of moles over a specific or a given volume. So if we can look at that, as soon as I increase my surface area, my concentration, and I keep my volume constant, then it actually means that my number of moles will also increase. I can actually say that the number of moles is directly proportional to the concentration. Higher concentration, higher number of moles. So if I have a higher number of moles for the same volume, you can think, in the same small space, there's now more particles, and these particles will now collide more often. So when we look at the collision theory, we will now know that the increase in concentration leads or comes from an increase of the number of moles. And back to the C is equal to N over V, we can say the C, is directly proportional to the N, but that is only the case when my volume is constant. So according to the collision theory, we need to explain it in terms of the particle motion and the collisions, and we need to talk about the effective collisions per unit time. So an increase in concentration of the reactant will mean there is now more reactant particles per volume. So there will now be more collisions, so there will be more bumping per unit time. And if there's more bumping per unit time, there's a possibility of more effective collisions per unit time. And when we have more effective collisions per unit time, it basically means that we have a higher rate of reaction. The reaction is now faster. That brings us to our next factor. Our next factor is only applicable to gases. So whenever you see pressure, think gases. So when we talk about pressure, we can look at the next question where we ask, why does an increase in pressure lead to an increased rate of reaction? How can that happen? Right, so when we talk about an increase in pressure, the first thing that we need to remember, and this comes from earlier knowledge, that pressure is actually the force per area, and we will say it's the force per unit area. And according to Boyle's law, we've also heard and learned that pressure is inversely proportional to the volume, or the volume is inversely proportional to the pressure. So, firstly, if I say that the volume and the pressure is inversely proportional, that will basically mean if I decrease my volume, so if I have that volume with my little particles in, and I decrease my volume, let's say to half of the previous size, and I still have the same number of particles. Remember, your number of particles must stay the same. Then it basically means in a bigger volume, I have less pressure because there's less collision, and in a smaller volume, I have more pressure. So I can say, when we look at pressure in gases, we need to always know that it is connected to the volume. A decrease in volume leads to an increase in pressure, and an increase in volume leads to a decrease in pressure. Here I show you that. I've got the same number of moles. Remember, the number of moles must remain the same so that we can say, in a fair experiment, when I decrease the volume, my pressure will increase. Right, so just to explain, why does an increase in pressure lead to an increase in reaction rate? According to the collision theory, we can now say that a decrease in volume leads to an increase in pressure because there's now more particles in that small space. So we have more collisions per unit time, and if there's more collisions per unit time, it basically means there's a likelihood of more effective collisions per unit time, which leads to a faster rate of reaction. So, all well, we're going on. We're going to the next one. We will go look at the next one. Why does an addition of a positive catalyst result in an increased rate of reaction? Now, we spoke about a positive catalyst before. We said it lowers the activation energy. If we can just look at an energy profile, if that is my activation energy, when I have a positive catalyst, I will have an alternative path, a path that leads to my product faster. Remember, it's the same amount of product, we just read product stage faster. So, provides an alternative path after lowering the activation energy. You need to know it's not used up at all in the reaction, or not used at all, and the same amount of product is formed. So when we look at the effect of the collision theory, we now know that if it's a positive catalyst, there will now be a lower activation energy. There will be more collisions per unit time. There will be more effective collisions per unit time. That leads to a faster rate of reaction. And again, only the time frame changes, but not the product. Product remains the same. Then we spoke about the nature of the products, in what group they are, the reactivity, that's important. In closing, I would like to remind you of the following. Reactions happen at different rates. Reactions can be fast or slow. It all depends on what we're reacting. There are different factors that affect the rate of a reaction. And we said, and we spoke about 6 of these factors. We spoke about macroscopically as well as microscopically how they affect the reaction. These factors can be explained by looking at the submicro view of a reaction. And when we look at the submicro view of the reaction, we spoke about the collision theory. So for now, that's me. Thank you.